In this video, we're going to look at one-way analysis of variance. Let's first remind ourselves about the relationship between init years, we're going to do the recoded init years, and refractive error. And we saw from before that we get this relationship that kind of goes downhill. Refractive error declines over time, but it's not linear. It has kind of this little curve here, it slopes and then goes down real fast. We fall off a cliff. There are no cliffs in linear data. So a regression, a straight line regression, may not be the most appropriate statistic for this relationship. Instead, we're going to do a linear model, but it's going to be analysis of variance, where we look at each mean separately and we don't assume that there is this linearity. And so the way we do that, and in this particular case, we're just going to do a general linear model. And the general, for a one-way ANOVA, we need to have there's a couple here. We have univariate, where there's one outcome variable, in this case refractive error. Multivariate, if we were going to look at, say, lens thickness and refractive error and axial length all at the same time as an outcome measure, not as predictors, but outcome measures and their relationship to that, and you kind of assume they all mean the same thing in a multivariate analysis. We won't really talk about this one too much. And then repeated measures. Now we have repeated measures in init years. In fact, init years are the repeated measures, but the our data is not set out correctly, and we don't have complete data for this. So again, we're kind of violating the assumption of independence when we do this method, but we're doing it just for illustration. So we're going to look at refractive error. We're going to do this the right way in a future video. But for now, this kind of will show us what we need to know. So we have a dependent variable, fixed factors. This is one-way ANOVA, so we only have one variable here. We could have a factorial ANOVA in which we would have several variables here. So in a future, we might do init years by ethnicity or something. Covariates are continuous variables that we would maybe put in here. Say we wanted to adjust for axial length or something like that. We could put that into our model. Under model, it gives us, this really defaults. We don't have to deal with this very much. Contrasts is actually kind of a potential one that we might want to look at. We can, but for now, I think we will not bother with that. The same way with plots, we're not going to really look at that, or post hoc analyses. There's, we will look at this one. Let's put that in there. We're going to look at least significant differences and the Reg-Wef one. We'll see what those are in a bit. We could save our predicted values and residuals if we wanted to. Look again at our leverage statistics that show if there's single values that influence the outcome. We'll pass on that for now. And the options are, and here's another one. It's it's basically like the post hoc, except it just has, you get the means and it gives you fewer options. Only the least significant difference test and the Bonferroni in the other. So we're just going to look at that one for now. We will look at parameter estimates, and we'll look at homogeneity tests to see if our variances are equal, and that will be it. I think I'll get rid of the post hoc tests. All right, here's our output. What have we got? This tells us how many subjects we have for each of the init years. This is our test of equality of variance. Rejects the null hypothesis, suggesting that the variance is not equal. So really, that's kind of a problem that we have. Our variance is not equal. And that's pretty clear from our box plot. You can see lots of variability here, not so much up here. So we could do a log transformation, but that just gets hard to interpret. For now, we're just going to go with it. The problem with this is in our post hoc comparisons, we're going to be too conservative in finding differences down here and too liberal finding differences up here, because we're going to take the average variability when we make our comparisons. Talk about that in a later video. Here's our tests. So is our init value significant? Yes. What this p-value is, this is the probability of finding an F statistic this big if the null hypothesis is true. And it's a very small probability. So we've rejected the null hypothesis. Which means are different? We don't know. All this F test says is there's a difference in there somewhere. We have parameter estimates. These parameter estimates are exactly the same thing as a regression equation. We have our intercept, and we've created dummy variables because this is a discrete system. Instead of one variable with a slope across all init years, we have basically a slope for each of the years, -5, -4, and so forth. Because dummy variables don't need all of the data, it uses this last year, +4, as the control. So all these values are with respect to 4 years. So the average distance or the average refraction change between 5 and 4 is 3.986 diopters. It's positive because the negative is given first. Here are estimates of diopters over the years. We start at about a ½ diopter, and as each year goes, these are myopes. It keeps going down, 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 down. So the average at 4 to 5 years after, the average diopter is -3.5. Then we ask for the comparisons, and so this gives us a pairwise comparison. Remember, the F-test just says that there's a difference somewhere, and this table does all the paired comparisons. So it looks at the lowest from 4 years, not quite significant, but it is significant from -7 through 5 is significant from 3 years on. -4 significant from 3 years on. Is different from 3, and then 2 on, and so forth. And you can see all the various paired comparisons. So that's how you do one-way analysis of variance.